Good day and welcome to Lecture 29 in Physical Chemistry 1. Just a reminder that we have a science seminar this week on Thursday, November 8. Patent Law for Scientists and Engineers by Connie Powell Nichols of the Law School at Baylor. So come on out for that, and I'm sure that you'll learn something. So today, this is lecture 29, but really at lecture 28, so this is kind of weird how the numbering is working. But we're going to be talking about rotational Raman spectroscopy, and Raman spectroscopy, really rho and vibration, so we'll talk a little bit about that as we go here. And you'll like this pretty much, I'm hoping. So there we go. So what we've been talking about of late: translation, vibration, rotational motion. These are the charmed ones, the power of three. Yes, yesterday we talked about rotational motion and rotational spectroscopy, and microwave spectroscopy sometimes call it, because rotational spectroscopy takes place in the microwave part of the electromagnetic spectrum. So this is our little review sheet for our modes of motion. You should know the translation, vibration, and rotations. You should know the energies, you should know the wave functions, and you should know the quantum numbers for each one of the different types of motion. And we have here both the rotation on the ring and the rotation on the sphere. So there we go. Today, we're going to talk about Raman spectroscopy and then vibrational spectroscopy, and then we're going to combine rotational and vibrational spectroscopy together to get what we call rho vibrational spectroscopy. In Raman spectroscopy, we look at changes in rotational energy, but we use it by a scattering technique where you have a source that comes in, a source that is a light source. There's going to be a laser of some monochromatic wavelength. Yes, that shines in, and then you have a sample here, and light is then scattered from this sample. Yes, all kinds of directions here. It's collected by this bunch of optics, and it sends those light wavelengths to a monochromator that separates them out and sends them to a detector. So one wavelength comes in, but many wavelengths come out, and they come out because the energy that goes in interacts with our sample to gain or lose energy based on the sample gaining or losing rotational energy. So if the sample gains rotational energy, the light will lose energy. If the sample loses rotational energy, the light will gain rotational energy. Okay. And so we get some wavelengths that are shorter because the light has gained energy, and some wavelengths that are longer because the light has lost energy because the sample has gained energy. And so you'll see as we go through here how this is all working out. The gross selection rule, as we call it, for Raman spectroscopy is for the molecule to be what we say polarizable. And there are quantifiable ways to define this polarization ability. Okay, but you can think of it kind of as the cloud of electron density being polarized in such a way as to sort of change what the dipole moment is kind of doing in there. Yes? So it's complementary to rotational spectroscopy, because remember, in rotational spectroscopy we required a permanent dipole. That is, the molecule had to have a polarity. In Raman spectroscopy, no, most of our molecules are not polar. They can be, but oftentimes they are not, because we can change them in a way that produces sort of a dipole in them by smushing them in a way or so. Okay, so it's a complementary technique to our rotational spectroscopy, to our microwave spectroscopy Raman is. But it's much more complicated to do than is microwave spectroscopy. But let's take a look at it here. And what you see is these lines that are produced. Okay, the lines are like this. Some are more intense and some go down. And you got a big bunch in the middle here, and you got some other ones going here. And then they go down. And so you get sort of a distribution that kind of looks like this. Now, what you have here is the Stokes and the anti-Stokes lines. And then the Rayleigh line. So Rayleigh lines, if we look back at the previous picture here, is light that reflects directly off of the sample and doesn't change its wavelength. Okay? So when the light reflects off the sample, the wavelengths could stay the same in that there's no energy absorbed or gained by the light. The wavelength could get longer if energy is lost, or the wavelength could get shorter if energy is gained. Yes? So the Rayleigh light is this reflection of light with the same frequency. Okay? So that shows up here in the middle of your spectrum. Boom, 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 right there. Yes? And the frequency of that light should be the same as the frequency of your laser that you're sticking in. Now, if frequency is going up, that means the wavelength is getting shorter. Yes, the wavelength got shorter. That means that the light gained energy, which means that the molecule lost energy. And these are the anti-Stokes lines here. And you see the change in rotational energy associated with this loss of rotational energy. So that means you had some energy maybe at a J equal 2 state, and it went down to a J equals 0 state. Because for Raman spectroscopy, the change in J is equal to plus or minus 2. Unlike with microwave spectroscopy, where the change in J is plus or minus 1. Okay? So the Stokes lines then must be the other one. The frequency is getting shorter, or longer, excuse me. Oh, no, the frequency is going down, so the wavelength must be going up. Yes, the wavelength goes up, we have less energy in our light, so the light has less energy. It gave energy to the molecule, right? So that means that it must have gone up in rotation, maybe from 0 to 2 or from 2 to 4. And all these then are different transitions from 0 to 2, 2 to 4, 4 to 6, 6 to 8, and so forth and so on. And so what you see is that there are some 0 to 2 type things, or 2 to 0 type things. There are more of these guys in the middle, and as you get to higher J's, they start to go down again because the distribution of energies in those higher states starts to go down again. Yes, and so this is the idea of Raman spectroscopy. You got the Rayleigh light, which is just reflection. You got the anti-Stokes lines and the Stokes lines. Okay? Frequency goes up. That means that the energy goes down. Alright, so I hope that helps you a little bit get an idea of what Raman spectroscopy is all about. In the old days, it was really difficult and took huge machines to do this. Nowadays, the instruments for Raman spectroscopy are much smaller than they used to be, but still kind of a pricey way to do things. And it's a more expensive instrument than your normal microwave type of spectroscopy for rotational motion is. But it gives you complementary information, so it's helpful that way. Now, let's move on to vibrational spectroscopy. Okay? So if you remember, our understanding of chemistry is that we have this electronic potential, and that our molecule vibrates about an equilibrium bond distance associated with this electronic potential. Yes, where this is the equilibrium bond distance, that our molecule normally is averaging about. It could be a little bit longer, or it could be a little bit shorter. Yes, and so it vibrates about this equilibrium bond distance. Okay? All right, so that's pretty cool, huh? Yep. Now, the idea here is that at the bottom of this electronic potential, it kind of fits a parabolic curve. Or there you got a parabolic curve where y equals what? X squared type of thing. Really, we know that it's not parabolic because it's not symmetrical in that the electronic potential looks more like that. But we approximate it with this parabolic curve, which is why when we calculated the vibrational energies in our quantum mechanical models, we used that Hooke's law, 1/2 k x squared, to model the potential. And we didn't introduce any anharmonicity effects into there. Well, we know there are some anharmonicity effects. But anyway, before we talk about those, let's just talk in general about the shape of this curve. Okay? Remember the potential if we have it 1/2 kx squared. If k gets bigger, then this curve goes up faster. And if k is smaller, then you'll have a wider sort of surface in there. Yes? So the bigger k, okay, k is big, it's going to be sharp and narrow. If k is small, it's going to be broad. Okay? And you can think of this as related to the strength of the bond that you're vibrating here. If you have a strong bond, it's going to vibrate pretty fast and furious if you try to stretch it out. If it's a weak bond, it's going to be kind of floppy, and the potential is going to be broad. All right. So think about the vibrations of our molecule. Here's a triatomic molecule, okay, like water or something like that. Or no, probably like something like CO2 if it's linear like this. And if it vibrates, this thing can move up or it can move down. Now, to be what we call vibrationally active for our infrared spectrophotometry, the gross selection rule, as we say it, is that we must produce a change in dipole upon vibration. So if in this particular case you got no dipole and there you vibrate such that now your dipoles are going to add or subtract to each other, you will be changing the dipole moment of your molecule, and this would produce then a vibrational spectrum in the infrared, which is where we're going to look for our vibrations. Okay, so that's the gross selection rule. Okay, so we're going to have these vibrations, okay, and they're going to be energy levels within our electronic state, and as we saw, they should be equally spaced. But because our spectrum, our surface, our energy surface here, is not a parabola, this equal space stuff doesn't stay equally spaced as we go up, but they get closer and closer and closer together because of this asymmetric part to our potential over here. And so what should be a change in energy that equals h bar omega every time as you go up an upsilon or a v if we talk about spectroscopy, we see that in fact that's not the situation. That as you go up, they get a little bit closer together each time as you go. And eventually, as you get near the what we call the dissociation limit of this surface, these guys get infinitely closer together. Yes? All right. Now, there's also a difference between what we call the D0 and the DE. Okay? Our DE is the dissociation limit from the bottom of the electronic potential. The D0 is the dissociation limit from the ZPE. Okay, so remember your ZPE here is where we have a 1/2 h bar omega, or a 1/2 h nu amount of energy. Yes, because we can't have zero vibrational energy. That's our ZPE. So the difference between D0 and DE is this 0 point energy. That makes them different. Okay. Now this little tilde thing on top and stuff, that means to say that we want to put this thing into wave numbers, right, or inverse centimeters, and you go back and forth between inverse centimeters and joules by multiplying and dividing by HC. Okay, so if we want, energy here in joules, we would take HC times our inverse centimeters, and we will get joules out. If we want to divide joules by inverse centimeters, then we'll get the wave numbers. Okay, so know how to go back and forth between wave numbers and joules via our conversion factor HC, where H is Planck's constant and C is the speed of light in centimeters per second here, not meters per second. Alright, well, that's cool and dandy and stuff like that. And then we can look a little bit at this sort of thing, and we can add up all these vibrational energies here. Here's the first step of vibrational energy, and the next, and the next, and they get closer and closer together. And this is what we call the thing that we built, or many of you built, when you did the I2 spectroscopy lab. This Berg-Spooner plot. Yes? And if it was good, Berg-Spooner plot, we get a nice straight line, but because of this asymmetric part of the parabola, it actually kind of goes down like that. Yes? But either way, you can plot up these Berg-Spooner plots, okay? And you can, find some things from it, which is kind of cool. Yes? Alright. Now, this is vibrational spectroscopy here. So you're just looking at the vibrations of the molecule within some potential well. Okay? Now, the molecule vibrates within an energy well. In I2, we put another potential well up there. Okay? And we go from one vibrational level to a different vibrational level up in the higher electronic state. And so you have a change in electronic energy, and you have a change in vibrational energy. Yes? And we also said in the I2 lab that there's also a rotational energy change, but we can't observe it because it's too small for our spectrometer to measure. But now we want to look a little bit at this combination of going from a vibrational state to another vibrational state. And as we change the vibrational energy, we want to look a little bit more closely at how the rotational energy also changes. Because within each vibration, the molecule also rotates. And these are little rotational energy levels in here. So you go to a new vibrational level, but you got little rotation levels in there. And the spacing between rotational levels is less than the vibrational levels. So, they're in there. And you can go from one vibration to another vibration, but you can also, as you do that, go from one rotational level to another rotational level. And that's what we want to look at next year as we talk about what we call rotational vibrational spectroscopy. Okay? So here we go. Here it is. Here is what it looks like. So what we have is that light comes in, and the molecule absorbs it, and it could just go from one level to another level. Here's our V equal 0 level, and here's our V equal 1 level. Okay. If we go from this to that, we could go from a 0 rotation level. These are the rotational levels within the vibrational levels. Okay, we went from a 0 to a 0. We would call that a Q transition. So Q is a 0 to a 0. Okay, or a 1 to a 1, or a 2 to a 2. But in all these things, what do we see for the change in the rotational? That is no change in rotation. Okay, we call those the Q branches. Now, oops, sorry, my bad. Here we go. Now, if, on the other hand, we go from a 0 rotation to a rotation of 1, okay, and that's this line here, if you can see it going from a 0 to a 1. So down here it has 0 rotational energy, but up here it has 1 quanta of rotational energy. As it changes 1 quanta of vibrational energy, we call that an R branch. Okay, so that could be from a 0 to a 1, or it could be from a 1 to a what? A 2, or it could be from a what? A 2 to a 3. What we notice is that the change in rotational energy, the delta J, as we said before, is always going to equal plus or minus 1. And if it's a plus 1, then we are going to see here what we call the R branch. Okay. On the other hand, the molecule could lose energy in rotation. So here we start from rotational level 1. There you can see it, and it goes up, 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 and it goes up to rotational level 0. There it is, 0. So in this case, the delta J went from 1 to 0, or it was a minus 1. So we lost rotational energy on this change in vibration. Okay. We call that the what? The P branch. So the P branch are losers with respect to rotational energy. The R branch are what? Winners with respect to the rotational energy. So our total change in energy, our delta E here, is equal to 1 vibration, okay? And then it's plus or minus 1 rotational change. Yes, that is plus or minus a delta J, or that delta J is equal to 1. Okay? So it could be a little bit more than a vibration, or it could be a little bit less than a vibration. Okay? But the delta J of 1 differs depending on which J you start from, as we saw before with the rotational spectrum. So even though we have these spectrums down here, where all these R's out here are for delta J's equaling plus 1, and all these P's are for delta J's equaling a minus 1, they're starting from different levels in the bottom. And therefore, the transition energy is different for each of those changes of 1, depending on where you start from. Okay, and so this gives us all these different lines that march out in the R direction or in the P direction. And even our Q's, even though although the delta J's are equal to 0, and you think there'd be no change in rotation at all there, because you're just taking a vibration, and if you're going from 2 to 2 or 3 to 3 or 4 to 4, you'd think it'd be no change in rotation, because the molecule is a little bit different in this higher vibrational energy. It might be a little bit spread apart. That is, its moment of inertia might be a little bit changed because it's stretching a little bit. Those Q's have a little bit of a distribution to them as well. Alright, now over there on the right hand side you see the effects of isotopes. Okay. Chlorine has strong isotopic effects. That is, about a third of the chlorines are chlorine 37s, yes? And so when you do the rotational vibrational spectrum of HCl, you can see both isotopes because they're going to give us slightly different energy in these transitions because the moments of inertia are going to be a little bit different. Yes? Still see the Q branch, but now you see two sets of P branches, one more intense than the other because there's more of chlorine-35 than there is of chlorine-37. And then you also see the R branches there where the rotational energy is increasing. And there you go. So that gives you rotational and vibrational spectrum here together. So as we change the vibrational energy, we might not change the rotational energy level, but we might gain some or we might lose some. If we go to the same rotational level in the upper vibrational state, then we say the delta J equal to 0, and we have the Q branch. If we have a delta J that's plus 1, we have an R branch. If we have a delta J that's minus 1, we have a P branch. Now, not every molecule produces a Q branch. Okay, so this isn't always present in every molecule. All right? Okay. So, keep that in mind as we look at different things here. All right. So, that's pretty cool, huh? All right, so what does that mean for us? Well, it means that for us today, we've talked about Raman spectroscopy, scattering of light and the changing of the frequency as a result of molecules gaining or losing rotational energies of plus or minus 2 J's. Talked about vibrational spectroscopy, in general, just changing vibrational energy. And then we said that really when you change vibrational energy, you might also change rotational energy. And so we talked about rotational vibrational spectroscopy and those P, Q, and R branches in things. And wow, that was a fun thing to talk about. So hopefully this helps you out with your homework. And what's it take to be a P-Chemist class? That's right, hard work.